Right now, without knowing it, you're playing a game. Not a game you chose. A game with rules you were never taught. And people who mastered those rules are making better decisions than you. In salary negotiations, in business deals, in relationships, in geopolitics. The tool they're using is called game theory. And it is not what you think. It has nothing to do with chess, nothing to do with video games, and nothing to do with being clever. It's mathematics. Specifically, it's the mathematics of strategic decision-making, a formal framework for predicting what rational people will do when their choices depend on each other. In the next 20 minutes, you will have the complete mental model. Let's go. If you watch the negotiation video, the one where we broke down BOTNA, tactical empathy, and the FBI framework, you already know something important. Those tactics work, but we never explained why. Why does mirroring someone's words make them trust you? Why does anchoring with a high number shift the entire conversation? Why does silence sometimes win more than speaking? The answer isn't psychology, it's game theory. Every negotiation tactic is a practical application of a formal mathematical principle. Today we go one level deeper. This is the engine under the hood. Chapter 1. What game theory actually is. Game theory is the mathematical study of strategic interaction between rational agents. That sentence sounds academic. Here's what it actually means. Any situation where your outcome depends on what someone else does, that's a game. Choosing a price for your product when your competitor can also change their price. Game. Deciding whether to confess to a crime when you don't know what your co-defendant will say. Game. Choosing whether to cooperate in a climate agreement when defecting could give you an economic advantage. Game. John von Neumann and Oscar Morgenstern formalized this in 1944 with their book Theory of Games and Economic Behavior. They wanted to create a rigorous mathematical framework for human conflict, something more precise than intuition, less chaotic than psychology. John Nash, yes, the one from A Beautiful Mind, later extended the theory to include what we now call the Nash Equilibrium, which we'll get to in Chapter 3. But first, you need to understand the basic unit of game theory, the payoff matrix. Chapter 2. The payoff matrix. A payoff matrix is a grid that maps every possible outcome of a strategic interaction. Let's build one in real time. Two companies, let's call them A and B, are both deciding whether to lower their prices. Each has two options: keep prices stable or cut prices. If both keep prices stable, both earn good profits, let's say $10 million each. If A cuts prices but B doesn't, A steals B's customers. A earns $15 million, B earns $3 million. If B cuts prices but A doesn't, reverse. B earns $15 million, A earns $3 million. If both cut prices, they cancel each other out. Both earn $5 million, worse than if neither had cut. That's the matrix. 4 boxes. Each box shows what both players earn depending on the combination of choices. Now here's the critical question. What does a rational company do? You look at your options. If B keeps prices stable, you earn more by cutting. If B cuts, you lose less by cutting. Either way, cutting is your best move. B runs the same logic, so both cut. Both earn $5 million instead of $10 million. They both made individually rational decisions that led to a collectively terrible outcome. This is not a thought experiment. This is every price war ever fought in the airline industry, the smartphone market, the retail industry, and the reason it keeps happening, the reason people can see the trap and still walk into it, is the Nash Equilibrium. Chapter 3, Nash Equilibrium. John Nash asked a simple question. In any strategic game, is there a stable point in a set of strategies where nobody benefits from changing their choice unilaterally? The answer is yes. and he proved it exists in almost every finite game. We call it the Nash Equilibrium. Here's the formal definition. A Nash Equilibrium is a set of strategies where each player's strategy is a best response to the strategies of all other players. In plain terms, you can't do better by changing your move, given that everyone else is sticking to theirs. Back to our price war. Both companies cutting prices is a Nash equilibrium. Why? Because if Company A is already cutting prices, Company B can't improve its outcome by switching to stable prices. It would just lose customers. Same logic applies to A. Neither side benefits from moving, so nobody moves, even though both wish they were both back at the 10 million outcome. This is why price wars last for years, why arms races are hard to stop, why traffic jams are structurally inevitable, why countries don't voluntarily reduce carbon emissions even when everyone agrees it would be better if they all did. The Nash equilibrium traps rational actors in collectively suboptimal situations. Here's the most important insight from this chapter. A Nash equilibrium is stable, but it is not necessarily good. Stability and optimality are different things. Game theory doesn't promise a happy ending. It just tells you where the system will settle. Now let's look at the most famous game theory scenario in history, one that puts this in human terms. Chapter 4. The Prisoner's Dilemma. Two people are arrested for the same crime. They're separated. No communication. Each is given the same offer from the prosecutor. If you testify against your partner and they stay silent, you walk free. They serve 10 years. If you both stay silent, you both serve 2 years. The prosecutors only have enough for a minor charge. If you both testify against each other, you both serve 5 years. Think about what a rational person does. You don't know what your partner will do, but you can reason through both scenarios. If they stay silent, you're better off testifying. You go free instead of serving 2 years. If they testify, you're better off testifying. You serve 5 years instead of 10. Testimony dominates silence in both scenarios. It's what game theorists call a dominant strategy, an action that is the best response regardless of what the other player does. But here's the trap. Your partner runs the same logic, so you both testify. You both serve 5 years, when you could have both served 2. This is why it's called a dilemma. Individual rationality produces collective punishment. The prisoner's dilemma isn't just a hypothetical. It's a template for some of the most consequential situations in human society. The nuclear arms race between the US and Soviet Union was a prisoner's dilemma. Both sides would have been safer with fewer weapons, but neither could trust the other to disarm first, so both kept building. Climate change is a prisoner's dilemma. Each country would benefit if every country reduced emissions. But any single country that reduces emissions while others don't just gives up economic advantage without improving the climate. So most countries defect. The critical variable in prisoners' dilemmas is repetition. This matters enormously. Chapter 5. Zero-Sum Games. Not all games have the structure of the prisoner's dilemma, where cooperation could make everyone better off. Some games are zero-sum. In a zero-sum game, the total payoff is fixed. One person's gain is exactly another person's loss. Poker is zero-sum. The money at the table doesn't change, it just moves. A salary negotiation is approximately zero-sum. Every extra dollar you get is a dollar the company doesn't keep. Trading in financial markets is largely zero-sum. If you sell high, someone else bought high. In zero-sum games, the strategies shift fundamentally. In non-zero-sum games, you can often find cooperative solutions that expand the total pie. In zero-sum games, there is no pie to expand. You're fighting for slices. The optimal strategy in many zero-sum games is what we call a mixed strategy, randomizing between options to remain unpredictable. Here's why. If your opponent knows what you're going to do, they can exploit it. A tennis player who always serves to the right is beatable. A poker player who always bluffs with weak hands is readable. Von Neumann proved, this is called the minimax theorem, that in every finite two-player zero-sum game, there exists an optimal mixed strategy that minimizes your maximum possible loss. This is what elite athletes, poker players, and military strategists do intuitively. Game theory just gives it a mathematical foundation. But here's the most valuable real-world insight from zero-sum thinking, recognizing when you're not actually in a zero-sum game. Most people treat negotiation, business, and even relationships as zero-sum. I win, you lose. But most of these situations are actually non-zero-sum. There are creative solutions that make both sides better off. The companies that figure this out build partnerships instead of price wars. The ability to identify which type of game you're in and pivot when necessary is one of the most practical skills this framework gives you. Chapter 6. Tit-for-Tat, an Evolutionary Strategy. Here's the question this entire video has been building toward. If the prisoner's dilemma traps rational actors in defection, why does cooperation exist at all? It exists because most of the games we play in real life are repeated. In 1980, political scientist Robert Axelrod ran a computer tournament. He invited game theorists to submit strategies for repeated prisoners' dilemmas, games played hundreds of times with the same partner. Every submitted strategy competed against every other strategy, hundreds of rounds per matchup, thousands of games total. The winning strategy was also the simplest one submitted, tit-for-tat. The tit-for-tat strategy has 4 properties. It's nice, it cooperates on the first move and never defects first. It's retaliatory. It immediately punishes defection by defecting back. It's forgiving. After one retaliatory defection, it returns to cooperation. And it's clear. Opponents can easily see and understand the pattern. Why did it win? Because it builds cooperation while protecting against exploitation. The nice opening establishes goodwill. The immediate retaliation eliminates any incentive to defect. The quick forgiveness prevents cycles of mutual punishment, and the clarity allows the other player to adapt. In the real world, reputation is your tit-for-tat strategy. When people know you'll cooperate if treated fairly and retaliate swiftly if betrayed and then return to cooperation, they have strong incentives to cooperate with you from the start. This is why trust-based businesses outperform transactional ones over time. It's why countries with long diplomatic histories cooperate more than those without. It's why your personal reputation across a career is often more valuable than any single deal. A more recent extension of this thinking is win-stay, lose-shift. If your current strategy is producing good outcomes, keep it. If it's not, change. This sounds obvious, but most people in organizations do the opposite. They double down on failing strategies because changing feels like admitting defeat. Game theory doesn't just tell you what's optimal, it forces you to confront what you're actually doing. Chapter 7. Applying this in 2026. Let's zoom out. Game theory gives you a framework, a way of structuring problems that previously felt like pure intuition, emotion, or luck. When you enter any interaction, the first question is, what type of game is this? Is it one-shot or repeated, zero-sum or non-zero-sum? How many players? What does each player actually want? Most people never ask these questions. They react emotionally, default to their habits, and wonder why they keep getting similar results. Second question. What are the Nash Equilibria? Where does this situation naturally want to settle? Because if you don't understand the equilibrium, you'll keep trying to push the system toward outcomes it will always resist. third question: is there a cooperative solution that current dynamics aren't reaching? If so, how do you build the trust and reputation to unlock it? These three questions apply to salary negotiations, to business partnerships, to international diplomacy, to how you structure your team's incentives, to how you set prices, to how you handle conflict in relationships. The honest limitation of game theory is that real humans are not always rational actors. We're emotional, biased, inconsistent. Game theory's predictions depend on the assumption of rationality, and reality often violates that assumption. But even accounting for irrationality, the framework is useful, because even irrational actors respond to incentives. Even emotional decision makers are constrained by their options and payoffs. Understanding the structure of a game helps you navigate it, even when the other players aren't playing perfectly. John Nash said that the best result comes from everyone in a group doing what's best for themselves and for the group. It took formal mathematics to prove why that's true and to show when and why it fails. Closing. The honest verdict. Game theory is not a cheat code. It doesn't guarantee wins. What it does is give you clarity on why interactions play out the way they do, and a structured way to think about how to influence them. You now know why price wars trap industries, why cooperation is harder in one-shot interactions than repeated ones, why dominant strategies exist, and why the simple, retaliatory, forgiving approach of tit-for-tat beats sophisticated manipulation over time. The question I want you to think about: which game are you currently playing as if it's zero-sum, when it might actually be non-zero-sum? Drop your answer below. I read every comment. And if you want the next subject in this series, in TRAS, we're building the complete mental model library. Subscribe and tell me what comes next. See you in 20 minutes.